Hey there, Miss Saturian here. We are on our next topic that has to do with waves, and it's going to be all about sound. So the essential question for this video is, what is sound, and how do the wave variables impact sounds we hear? And so we'll focus on a couple of different variables for this video here. And so let's start about what sound truly is, actually. A sound is basically a series of longitudinal pressure pulses. And so if you don't remember what that longitudinal type of wave is, go back to our wave properties video and see if you guys can kind of do a quick little recap for that. So sound can actually travel through any mechanical medium. It could go through air, it could go through water, it could go through a rock, whatever. And so these sound waves can travel through all these different things. The human ear has actually evolved over time to detect some sounds. And the human brain has also kind of learned to categorize these different types of sounds and interpret them into kind of like what we hear and like the languages that we end up speaking. If you were to look at a speaker itself, it could be in your phone, or it could be an actual like physical like portable speaker. In that speaker, there's a cone that you could actually put your like hand to and feel the vibrations of the sound waves. And so in this image, it would be like right inside that like the speaker itself. And what happens is these little pressure pulses, or like these are basically created of sound, and they move through the air to get to your ear for you to be able to decode and make meaning of what that sound actually is. And so it's just those little pressure pulses. Now, sorry for some of the funky looking images on here, but what actually is the wave source? And so almost anything can actually make a sound by vibrating the air around it or the medium that it's in. Every wave has to have a wave source for sound. In these like few examples here, these crickets on the top left, they actually make noise by rubbing their legs together, and that rubbing sensation, it vibrates. That movement creates vibration, and that actually makes a sound wave. The tree, I'm sure you guys have all heard this saying before, like if a tree falls in the forest and nobody's around, did it make a noise? Well, I'm here to tell you, yes, it did. So here's the thing. When you hear a sound, or when a sound is created, that's a vibration, like those little pulse like pieces that I was talking about. And so what happens is that vibration is happening whether we're there or not. So that sound is actually created. Humans, that's this nasty picture on the bottom left, which you should all be thankful for having, because that actually allows you to have a voice. And so those are your vocal cords right there. And so the two flaps that you see, air basically comes out of those flaps, and that movement of that air creates that vibration, which allows for you or any of us to have that voice. And maybe one of you guys can check on this last one for me, but giraffes actually might be the only animal that actually make no sounds. And so, yeah, maybe look into that one. All right, so let me kind of go a little bit over of how the ear actually works, mainly because there's a good reason why all these pieces are there in your ear, and they have a specific, duty for you to be able to successfully hear something. And yes, I said duty. All right, so let's start out with the main pieces. The pinna is actually like a funnel, and it collects sound that allows that sound to go into the ear. So that's basically this part right here. That's your pinna. The earwax, which would end up kind of being all up around in here, would actually have there's a good reason why that earwax is there, it is a dust trap. And so it keeps your ear actually free of like larger objects that could hurt some of the other parts of your ear. Let's see, the eardrum is this little thing right here, and it kind of looks like a drum. It is specifically called the tympanic membrane on this image, but it acts like a drum. It's a flap of skin across that entire part of that ear. And when the air hits it with the sound waves, it causes that eardrum to vibrate and create that and that allows for you to hear that sound. Right behind that, there are this funky little part right here. There are these small bones actually. And those bones are basically, what happens is like when the eardrum vibrates, so do these bones. And so what happens is it causes something else to happen in your ear, which I'm going to get to in just a sec. But those bones are actually the smallest bones you have in your body. Let's see, the cochlea, which is this funky purple looking thing in this image. Actually, I'm not sure like what color it truly is, but this itself is like a gigantic water balloon in your ear. It's got a lot of different fluids in there. But when that bone that I was talking about hits the cochlea, it makes it jiggle. And what happens after that, this part right here, these are nerves that are attached from this cochlea. Basically, it's attached to that, and then it sends like messages and to your brain to get you to understand what sounds you're actually hearing. And so that's truly what's going on with your ears when you hear a sound kind of coming in. All right, this next piece, let's go a little deeper into your ear. This is actually kind of like an inner ear image, and all this right here, oh my gosh, so grody. These are tiny little hairs. So in this cochlea, this is that cochlea, there are tiny little ear hairs, some long, some short, but these ear hairs are actually key. They're really important because our brain detects the frequency of a wave. If something has a high frequency, it's going to sound like this. If it has a low frequency, it's going to sound like this. And so the longer ear hairs in that cochlea will pick up the lower frequencies, and the lower frequencies will make it jiggle. And that's what you hear. The higher frequency is going to be those shorter hairs, and it's going to make those jiggle. And that's how you are able to get that sound information to process in your mind. One other thing that could happen is that it can detect the amplitude of a wave, basically how much energy that wave actually has. So there's all these little things that, like in your ear, that can do a lot of different things to allow you to be able to hear a lot of different types of sounds. And so on here, let's see, I wanted to double check. No, I got all the things you guys needed on here. All right, so for this next piece, I wanted to talk to you guys real quickly about kind of frequency. It's basically kind of how many how many vibrations there are in a second in that wave. And so humans interpret frequencies as pitch. So something with high pitch or low pitch. And so one thing that happens is with low frequency waves, that basically means that there are a low number of vibrations every second. High frequency means there's a lot of vibrations, a higher number of those vibrations from the sound wave in every second. And so low frequency is connected to low pitch. So a low frequency wave, that less vibration every second, is going to create a low pitch sound. And then a high pitch sound or a high frequency sound will sound like this. Imagine if I sounded like this all the time. So try this actually. Do something like this. Take your hand and put it along your vocal cord on your neck and start talking and see if you can feel the vibrations in your neck. And try doing like a low vibrate or like a low voice or a high voice and see if you can feel that change in the vibrations a little bit. And we'll kind of come back to that in a second too. Let's see. Typical hearing range for humans is actually like it can go anywhere from 20 to 20,000 hertz. And so something like a 20 hertz frequency for a sound wave would end up sounding very low like this compared to something that's at 20,000 hertz that's as high as this. So yeah, our voices are an amazing thing. Let's see. All right, we got our next little piece. We're almost done here. When we talk about amplitude, remember we're talking about the amount of energy in a wave. And so a higher amplitude sound wave is going to have more energy in that wave. More amplitude means that the medium, like let's say air, or like, and we'll stick to air for this one, it's displaced more, okay? So if we have a strong sound wave going through the air, in this example, in like a one that has a lot of amplitude, the air has a stronger pressure pulse. Basically, what this means is, let's say if I were to make that a noise that goes through the air, I put more of that energy into the sound, and that squishes the air into these tighter packets. Now, a lower sound would be something that has a low amplitude. And so we end up like comparing that high or low amplitude with volume. And so when something has a lot, like a high amplitude, we're thinking of the volume being high up. Okay. Now this image down here is actually, it's someone from the Coast Guard that is using this, this machine called an LRAD. It's a long range acoustic device. It's actually like a weaponized sound. And so it's something that is able to create an extremely loud noise, and it could actually rupture your eardrum. The Coast Guard used to use it against pirates when pirates were a big thing in the last decade or so. And the pirates ended up getting smarter, and they started wearing like noise canceling headphones, and so it wouldn't impact them. But something definitely more controversial nowadays is the fact that a lot of different types of law enforcement tend to use this as a crowd control mechanism, like during protests and riots. And there are definitely, this has been in the news in the last year about how there's a lot of like, I guess, countries or places that are fighting back against this, saying this is not okay to use against people. So if you're curious about that, look it up and see if you guys can find any other like updated info about that. All right, this last piece that I'm going to go through has to do with sound velocity. Now, this is tricky because people think that sound has a speed, and sure, it does. In air, it's a certain speed. But in, let's say, glass, it might be another one. In a rock, it might be another one. So it really depends on the medium that sound wave is going through, okay? You can't change the speed based on that frequency or that amplitude that I was talking about. You can only change it, that speed or the velocity, in a different medium. Now, imagine if I did this. If I changed, if you, let me rephrase this, hang on. If we were able to like change the velocity of waves in different mediums, if you were at a concert, different frequencies would get to you faster or slower. And so imagine you had all the low frequency waves coming to you at one point, and then the high frequency waves, like sound waves, coming to you at another. The song would sound really weird and funky. Think of it like this also. If you can't whisper and then a second later shout and have the shouting pass the whisper. That's not how it works. They'll get there, like the whispering will get there first because you started whispering first. Now in this image, you'll see like on the right, it gives you an idea of how like waves, like how the velocity is different from one to another. So in solids, actually, they move the fastest, and it has to do with the chemical bonds that make up that object. So the chemical bonds in a solid are tightly packed together. And so it's not easy to move like them around. And so what happens is the wave will go quickly through that solid object, okay? A liquid, not as fast. It's about maybe medium speed. And it's because those chemical bonds are not as tightly packed together, okay? They're a little looser. So it actually takes a little longer for that sound wave to pass through that liquid. And then the gas, if the medium or the sound wave was to move through a gas, it's actually the slowest. And for the exact reason, the opposite reason as a solid, the chemical bonds are very loosely packed together. And so it takes even longer for that wave to travel through there. Let's see. A couple of other things. You as a human, your ears can't tell how long you like a sound wave is, but your ear can actually detect the difference in time it takes for a sound to get to one ear than the other. And that's why we have two ears. If a sound is, let's say, coming from the left side of the room, it's going to hit your left ear first, but your brain can actually calculate the difference in time it took that sound to get from one ear to the other. And then your brain can actually work backwards to calculate a general location of where that sound came from if you couldn't see. Our eyes do something very similar, but we're much better at it. This whole idea is used in with your ears in the music industry and music videos and movies, where like a good way to experience this is you might be able to get sound to like one ear versus the other. Like when you have headphones on, certain sounds come into one ear, and they do this specifically to create more impact with the music that you're listening to. All right, so that's it for this video. Oopsies, there we go. Here's your essential question again. What's sound? How do the wave variables impact the sound that we hear? And there you have it, y'all. I hope you have an awesome rest of your day.